Okay, so good morning everyone, and thanks to the organizers for this nice workshop. So I'm going to talk about diffusion models, which is a way to do generative AI, and it's closely linked to a method in quantum field theory called stochastic quantization, which anyway makes the connection with the topic of this workshop. But in fact, the connection is much broader because it all has to do with stochastic differential equations, Brownian motion. So there's a very deep connection with things we as physicists know very well. So it's a great way to get into particular machine learning. Everything I say is based on things I learned in collaboration with my collaborators. The first paper was from September 2023. And then talk a bit about work with Dia, who's in the audience here. And then we had a very recent paper, which I briefly mentioned. So these are if you read these papers, you know as much as I do. And I just like yesterday, I think it's, I'm going to start in the same way as Jim and Zohar, that really machine learning is super interesting for theoretical physicists because a lot of the concepts that appear in machine learning are very familiar to us. And you can view this from many different ways. So a neural network you can see as a statistical system with fluctuating degrees of freedom. You can take the system very large, you can take a finite limit. As Dimitri said yesterday, there can be phase transitions. So we should be able to use our statistical mechanics ideas to understand neural networks. Training is a minimization process with stochastic dynamics. And of course, we know about stochastic dynamics, we know about minimization to find ground states of large systems. So again, there's a very close connection. And then, of course, the tools, the ingredients in all the machine learning algorithms are matrices and nonlinear functions, which you know very well as well. And so these are really the keywords. So machine learning is a new playground. So even if you don't apply it to something practical, it's still an interesting playground just to play with. So that's also one reason we do theoretical physics, because we work on interesting problems. And so really, this is kind of the way that I view it, or we review it. So you can think of neural networks as statistical systems. There's stochastic dynamics, which then leads you to random matrix theory. And tomorrow I'll give my second talk, which will be really on the random matrix theory aspects. And then you can think of learning as a kind of non-equilibrium evolution, not in, as the question was asked yesterday, in Minkowski time, but in some additional time during which you either you train or you generate configurations. And you can think of the end of learning maybe as some kind of thermalization stage where you find you minimize some cost function. And then if you take this a bit further, also there are, of course, as mentioned yesterday, you can have phase diagrams of neural networks. So on the axis are certain parameters like the width of initialization of the matrix element upon initialization, or the effective level of noise in the system. And there's this connection with spin glasses as well. So this is a very general setup, but it's definitely motivating for me to think about machine learning in this context. So in this talk, I'll talk about diffusion models. And then make the connection between diffusion models, lattice field theory, and statistical field theory. That's the goal. And like yesterday, please ask many questions. Just interrupt whenever you want. The first bit of the talk will be kind of introductory. Some basics on stochastic differential equations, for those of you who are not familiar with it. Because once you understand this bit, then the rest kind of falls out very naturally. So that's the kind of nice thing about diffusion models. And then I'll point out the relation between diffusion models and stochastic quantization, which is actually the way I got into this field, because my two collaborators on the first paper, so I've worked on stochastic quantization in the past quite a bit, so they contacted me and said, we would like to work with you because there's a connection. So that was really good. And then in the third part of the talk, I'm going to look a little bit closer at what diffusion models actually compute, because in field theory, we are not interested in pictures of cats and dogs, but we want all the higher order correlations to be correct, because that's what the interactions are in field theory. We want all the endpoint functions to be correctly represented because then we can make precision predictions. And so we'll look in much more detail about what the diffusion model actually computes beyond just the variance of the 2-point functions. Okay, so I have a lot of pictures of dogs, just to keep you focused. So this is the basic idea of a diffusion model. It's a generative AI approach. You take data, so it works with a data set, not with a distribution which is given to you, but with a data set which is given to you, say this data set of dogs. And in the so-called forward process, you then apply noise to these pictures. And so the dog is scrambled out by the noise. And then you go back. So during this forward process, the idea is that you learn this probability to transition amplitude from one picture to the next. You learn during this forward process. And then if you use those transition amplitudes in another stochastic equation going backwards, you regenerate pictures of dogs. That's the whole idea. And this picture in particular, so there's a lot of pictures where it goes forward and backward with the same dog. But the whole point, of course, is that you generate new pictures with new dogs. And so this dog is different, but it's generated using the transition amplitudes computed on this distribution data set. So that's the idea. And in the first 5-10 minutes, I'm going to show essentially this process in different ways, just to make sure that we fully have it understood.
So for physicists, the aim would be to find an S matrix and general principle between all pairs of dogs.
Not all pairs of dogs, but it will even in the next 5 minutes it will become clear. Yeah. So these diffusion models are used in the big machine learning algorithms. So DALI, Stable Diffusion, use this approach, and these are pictures taken from the almost original papers. So these are the papers that really clarified a lot, say. So, and one thing which is interesting if you do theoretical physics, that these papers are 5 years old, not 15 years old. Yeah. You can interpret that anyway. So this is the paper on the right. It exactly does this. You have trained your diffusion model and you generate phases. The one down here is used for interpolation, so you interpolate from one phase to the next to another phase, and they use what is called this. The main topic will be this gradient of the data distribution, or score-based generative modeling. Those are the key words. Now, to make the connection with physics, now we want in physics. So my background is lattice field theory, which is based on generating configurations and computing average of these configurations. And so you can look at this as generating configurations, not of phases, but of field configurations. And in fact, that's what we did in the first paper. So here is a similar plot of scrambled data initially. And if you run it, the process, you generate field configurations here, which you can then use to do statistical analysis, compute observables, and so on. So this is for a 5⁴ theory in 2 dimensions on a 32⁵ lattice. And I'll discuss this in much more detail later on, but this is just to have in mind that so Gen AI methods often have to do with real-world applications, but you can immediately translate this into an application in physics or computational physics, where we want to generate configurations from noise, and then use these configurations to compute observables. So that's if you don't like faces or dogs, that's the application.
So just to be clear, you start with noise, but then in the right-hand column, you have something which is drawn from the correct distribution.
Exactly. That's the statement we have. That's the conjecture. Exactly. That's the conjecture.
The case that you don't know the right distribution.
This is a very good point. In this case, we do not know the right distribution because we do not know the distribution of all faces. But if we apply it to a physics problem, we know the theory we want to simulate. And in fact, in our most recent paper, we then included an accept reject step here based on the exact distribution to make sure that the algorithm becomes exact. So in physics, we can do a bit more because we know the theory we want to simulate.
Yeah, but the crucial point is your second bullet point, right? That the training data is generated by hybrid Monte Carlo, which uses the action of the
That's right.
of the field theory.
Yeah. So that can be seen both as an advantage and a disadvantage. The advantage which you're hinting at is that you start with configurations which are distributed correctly. The disadvantage is that you have to generate those configurations, which makes it expensive. And so what we are working on is to implement this idea for field theories where it may be expensive to generate configurations, but then you supplement them by this approach, which is cheap. So that's the.
Maybe you'll comment. Will you comment later on the comparison of normalizing flows?
No.
Maybe it's how does this do compared to the normalizing flow work, which
It's,
I guess does not have the HMC training data, but doesn't use the power of diffusion models.
the main difference indeed is that normalizing flow starts from a target distribution, which is an analytical distribution. And so you don't need training data, which is a big advantage. The downside is that you then can suffer from mode collapse because you don't sample the space correctly. But that problem of mode collapse doesn't appear here because we sample the whole space. And the standard normalizing flow is not very stochastic, which seems to be a problem. Stochastic normalizing flow seems to be improvement on that. But I won't talk about normalizing flow. So.
And I guess in both cases, you mentioned if you want exactness, you just pick a clear line of shade and uses.
You always, so the exactness step is always a Metropolis Hastings type step. So now I'm slowly going to add some equations to this basic idea. And so it's based on stochastic differential equation. So the forward process is a Wiener process. It's written like this, with some force potentially and a noise, and the noise is time dependent. The strength of the noise is time dependent. In fact, this quantity increases with time, so to make sure that you really scramble the data very well. And then the trick is that when you go back, in the so-called backward process, when you regenerate the dog, in this case, it's the same dog, there is an additional drift term in your process, and this drift term is this gradient of the log of the distribution, or so-called score. And the point of where machine learning comes in is that we do not know this score a priori, but we can learn it from this forward process. So it's based on the transition amplitudes going in this way. That information will tell you this quantity, and so then you go backwards.
What is some kind of continuing thing?
Yeah, so in fact, I have a slide where I say I won't be very formal, I'll just use continuous time. So I prefer to work with continuous time, and but indeed, so there is a so-called, there's a certain discretization here, which is non-uniform, to make sure that everything is covered well. But we'll come, I'll do that as these indeed. And if we now talk about distributions rather than pictures, then this is the idea. This is the data set, P naught, which is,
In the previous slide, X was the space of images. If it says X, the vector X is the image.
is the image, yeah.
So it's this is diffusion in a very, whatever, in a high dimensional space.
It is a very high dimension space. And so if we just have 1 degree of freedom, and so we can draw the distribution, and we can draw samples from this, well, we have samples from this distribution, even if we do not know it. And the idea is that in the forward process, the information is erased, and we get something that looks like a normal distribution, although I'll discuss that this is not entirely correct. And then you reverse the process. You could start with a normal distribution, and you revert this process, this backward process, and you end up with new configurations from your target distribution. That's the
The second word GFT has some kind of noise.
Oh, sorry, yeah. So for those, so this is written in continuous time now. This is a random noise variable. So Gaussian zero mean variance 1. This is the square of this diffusion coefficient, which tells you how strong the noise is. It's a time-dependent function. But I'll do SDEs in detail because we don't do SDEs and we don't teach SDEs in physics so much.
And essentially, you're saying that this variation equation can be inverted.
Exactly.
And that's the invert.
That's the exactly. So we can create something from nothing. Mind-boggling, isn't it? But it is because we have a drift, an additional term in the drift here, and the drift will guide you to a distribution. This is how
B tau phi means exactly what? It's the At time tau,
So it's-
is it that B tau of 5? What exactly does that mean?
that is exactly this transition amplitude at time t here.
Transition amplitude or a probability?
No, it's a transition amplitude from t minus 1 to t. So
So shouldn't it have 2 phi's? What another?
let's go to the equations then. Okay, so all these questions are very good because it means it makes sense to talk about the basics to make hopefully everything clear. And so we have basically 3 ingredients. We have the target distribution, we have the forward stochastic process, and we have the backward stochastic process. And I'm going to talk about each of them, starting with the forward stochastic process. Now, there are 2, just to make a connection with the machine learning literature, for those of you who have looked at the diffusion model, there are 2 main approaches, and I'm just mentioning them here because these names appear a lot when you look at papers. There is something called DDPMs, which is denoising diffusion probabilistic models, or so-called variance preserving schemes. And then there are variance expanding schemes. And these can be treated in a unified way using SDEs shown in the paper. And so at the end of the introduction, I'll come back to this just to explain where the differences lie. So this is more for, as soon as you start Googling diffusion models, you will encounter this terminology. And as I said already, you can use all kinds of different notation, Brownian motion, renal process, continuous time. So I prefer to use the physicist approach and potentially not be rigorous, but still be correct. We are a physicist. So here's just 1 degree of freedom, x. X depends on time. There's a process here. K is the drift or the force. Eta is random noise. So the mean is 0 and the variance is 1, not correlated. And if we want to use this, so this is Brownian motion. This is Einstein 1905. If we want to describe an equilibrium distribution, e to the minus s, then we know that we can take the force to be the gradient of the log of this distribution, so the derivative of s prime, so minus s prime. And this I want to show in 2 slides or 3 slides that this will generate the correct distribution. So it's very simple discretization. So here is where I'm using really low-level math, no Wiener process or anything. Just discretize this equation with a step size epsilon. And the only peculiarity of SDEs is that the noise gives a square root of epsilon. This is the way it works in the Wiener process. So this is a very simple equation. You can iterate on your computer and update. And this will generate a trajectory of x in time. And what we want to do is to express this dynamic knot as this collection of trajectories. We say this can be described by the evolution of a probability distribution, P of x and t. So we can replace an average over the noise, over the trajectories, by an average over this distribution function. And given the question yesterday, the t should be here. And so if you do this, if you replace the noise average by an average over the distribution, then if the degree of freedom satisfies this Langevin type equation, this distribution satisfies the Planck equation. And I'm just going to derive it in 1 slide because it's easy and it's nice and supports what we're thinking. So let's take an observable O at 2 different times, n plus 1 and n. And if I use this discretized stochastic differential equation up there and I expand O of x plus 1 around x of n, then I have a first derivative, which goes with the drift and the noise. And I have to go to the second derivative because the noise goes with square root of epsilon. So this gives a term which is also order epsilon. And then all the higher terms are order epsilon over higher power. So I can ignore those. And if I then put brackets around it to take the noise average, so I take the difference between these 2, put brackets around it. In this term here, the noise drops out because the mean of the expectation value of the noise is 0. So I just have the expectation value of this derivative times the drift. And then this term is also order epsilon, but the expectation value of the noise is 1. So this simply gives a second derivative. And then I can have I have a discrete difference here, but I have a step size epsilon in both terms. So I can make take epsilon to 0 now. So the difference between these is the time derivative. If I divide by epsilon, it becomes a continuous time derivative. And then I can replace the expectation value of the noise by the expectation value with P and do some partial integration to let the derivative not work on the operator, but on, here it still works on the operator. But then if I do a partial integration, I can let the derivative work on the distribution. And since it has to be true for all observables, this gives you the equation for the distribution of degree x at time t. So this is the Fokker-Planck equation. Now this equation is very interesting equation actually. It's in general it's very hard to solve. But if we take the drift, if we assume or we say that the drift is coming from the gradient of the log of the distribution, then it's very easy to see the stationary distribution. Because if I say, if they're an equilibrium distribution or a stationary distribution, if I fill in what the drift is, so we get to this equation here, then you can immediately see that this is indeed the stationary solution. And so that's the point of stochastic differential equations, that if you have a drift, which can be derived from a potential or a distribution, and you run the stochastic process long enough, the system will thermalize, equilibrate, and the distribution of the degrees of freedom will be according to this. And that principle we'll use in diffusion models as well, but we'll introduce some new ingredients beyond this. Namely, the noise strength will be time dependent, so there will be an additional factor in front of the eta term, which will then appear in the Fokker-Planck equation. And also the force will be time dependent because we have this process where we guide the evolution from to the target. Yeah.
There were attempts to do sampling like this, basically learn the full score and run it to some equilibrium. If that was ever used before these non-equilibrium inverse diffusion stuff.
Well, it's in field theory, this is exactly called stochastic quantization. And in machine learning community, yeah. So the first papers are from around 2016, but they build on papers from the past, which somehow were not successful in the sense that it didn't scale, didn't converge, or not tractable, blah blah blah. So I'm not, I don't know the history very well. The current approach, the way diffusion models are currently done, obviously we're that's a way to do it because of this. Okay, so this is the standard. Anyway, this is SDE 101, and you have a Langevin equation, stochastic equation with a drift term, and if you run it long enough, you will equilibrate to some distribution.
Start with a discrete process.
Yeah.
Then you add some transition probabilities from xn to n plus 1, right?
Yeah, so in this, up to this point, in this particular step of the talk, I just have a fixed drift. My drift is simply the derivative of the log of the distribution. Rho is fixed. And so this means that if I run it, I will equilibrate to e to the minus s. And now we'll go to make it not fixed, make it time dependent and learn.
Of the probability from which your sampling initially changes as you add this noise.
Yeah.
You end up with some.
Okay, so the point is that if I have a drift term like this, I will end up with e to the minus s. If I don't have a drift term at all, I'm just doing diffusion, and I will end up with the normal distribution with an increasing variance if this is time dependent. With the drift, you converge to a prescribed distribution without diffuse. But this will affect all of this.
So let's say your S was, the attractive potential of some sort, then you start with something, an arbitrary point, and you feel a gentle force, and eventually with a little noise, and end up somewhere in the well.
The probability determined by this.
Well, if I take the histogram over different runs, I'll get a probability distribution, right? but in a given one, it'll end up somewhere. So,
Noise, so it runs somewhere.
and for images, we know it works the same way. The distribution of images, that one is allegedly, and then a particular one is some particular position in the web, that every different run will produce.
An image is one point in this way, one run in this way. So in machine learning, we want to cover the data set. So now we come to the kind of machine learning stuff. So, but not really, but we want to make sure. So we start with the data distribution, which is in a high dimensional space and which can be very localized. And so we want to make sure that in this forward process, we really cover everything, make everything noisy, so to say. And for this reason, you add a time-dependent noise, which grows in time. And then the Fokker-Planck equation is modified so that if you also introduce it in the drift like this, it's there. And so from the perspective of theoretical physicists, this is just a reparameterization of time because you can absorb this in the time of the drift. But from the perspective of machine learning, different choices of this strength of the noise here are called noise schedulers. And there's a whole machine learning engineering section where you try to optimize your noise schedulers. From our perspective, it can just be absorbed there. And then, okay, this was 1 degree of freedom. Of course, we like systems with many degrees of freedom. The distribution is then a functional. Think of a Euclidean path integral, for instance. And the stochastic process is then takes the same form. And so yesterday was a question about what is time. So this time here is not, of course, Minkowski time or Euclidean time. It's also not training time, but it's essentially the time in a computer simulation, like Monte Carlo time, when you do numerical simulations. And so this is a field equation, a four-dimensional field theory with time in the fifth dimension where you generate order configurations. And the Fokker-Planck equation that goes with this equation, and it's a functional Fokker-Planck equation, which takes this form. So these are functional derivatives. And in general, of course, we can't solve it. And the equilibrium distribution is the same. If the drift is derived from this gradient of this quantity, you get S prime here, so the proper equilibrium distribution. But this equation, obviously, or you also can't visualize it. So that's why we go to 1 dimension, 1 degree of freedom. Underlying all of this for field theory applications is this type of problem. Well, this is suppose you want to do a Euclidean quantum field theory, right. Then you would take that distribution and take the computed drift from that term, just to illustrate. This is just to illustrate that in general we work with functionals, and the Euclidean path integral is the one that you all know.
That's it. E0 or
so yeah, so this is more general. This is not specific to the diffusion process. This is just to say, in general, we don't have distributions of 1 or 2 degree freedoms. In general, we have functions. That's all I'm saying. Yeah. Okay, so let's look now more in detail about these evolving distributions. So now we solve some examples by hand, so to say. And so let's talk about the forward evolution. And I'm taking the very simple case here of no drift term. So just the noise from the normal distribution and time-dependent strength, noise strength. One profile that's often used is this one, which grows large. And then the other thing, which is interesting compared to how you normally think about SDEs, normally you want to run for a very long time because you want to equilibrate and then collect information in time. Here you really only want to run for a finite time because you want to run from time 0 to time capital T. And here you learn your transition amplitudes and then you want to go back. You don't want to take this capital T to infinity. So the difference compared to other time applications is that our time will always be between 0 and some capital time T. And that's the reason why it's as well. Now, this equation is very simple. This is an equation you can solve. You integrate over the noise. This is the initial condition. The variance grows. So this is an example of the variance expanding scheme. If you look at the variance and you put brackets around it, you get an average of the noise. And so you end up with a variance that grows like this for any noise. So what does it look like in practice? I have some initial distribution now, which is 2 Gaussian peaks. And I'm just adding noise to it. And I'm showing here the solution, not from the Langevin trajectories. I'm showing here the solution from the Fokker-Planck equation. And so I'm adding this noise here, and then just goes like this. So it erases the 2 peak structure, and it becomes something that looks very much like a normal distribution. If everybody spends time making movies, I'm going to show it twice as well. It's much easier than the ones shown yesterday. And this is actually written in terms of this transition amplitude that you asked about. So we split the description in terms of the target data, and then this is the transition from x0 to x. And this one, for this particular process, can be written down analytically. It's like Feynman's transition amplitude, also for those like theory. And in this particular case, all the time dependence is captured in the variance. And the point is, of course, is that this is the forward process, but the structure, which is 2 pieces. Now, backwards, we want to regenerate those 2 peaks because that's our data set. Our data set is. So how do we get structure emerging from noise? We add this extra term, the score, and this is a so-called Anderson equation. And this is, in fact, very old, 1982. So this has to do nothing to do with machine learning. This has to do just with Fokker-Planck equations, Golomb-Gorov equations, forward backward equations. So this is just a topic in stochastic differential equations. So if I change now, I have the drift still, I have the noise still. I'm going backward. Oh, this should be a tau. Can I write on this? But there is an additional term here, which is this gradient of the log of this distribution. So I won't prove this, but this is the statement that the corresponding backward equation has this additional term here. And we know what this transition amplitude is, in fact, because it's this quantity. So we know what to put in. Jump like this. So I skipped this slide. Okay, I see. Okay, this is more an aside. So we split this process in the initial distribution and this transition amplitude like this. And this is kind of a clean separation because this one we typically do not know. This is the collection of all cats and dogs or faces. Whereas this one, for this process, we know it's a very clean split in those 2. And then there is something called the manifold hypothesis, or so that if you look at real-world data, it is concentrated on low-dimensional manifolds in a very high-dimensional space. And so in this forward process, you want to make sure you cover all of those localized data, low-dimensional manifolds, which means that this noise has to grow strong enough to really capture all of those data structures. Kind of machine learning speak, so to say. That's the reason why you grow there.
This is related to something that I also asked. As you add noise, how do you know you're staying on this manifold? Or
You're not, no.
But then, okay.
You cover the whole.
The ambient, the
ambient
entire space.
The entire space, yeah. Okay. But the point is then when you reverse, you cover the whole ambient space. When you revert it, you will revert back.
Like it's different. The end of the forward process, but you mean the entire.
This one.
Yeah. Okay.
Yeah. So manifold. Yeah. Okay. Yeah. So the entire manifold in which the data lives in this space.
So you mean the real world data is concentrated on low-dimensional sub-manifolds?
Yes.
Manifold.
Yeah. Okay, so the Anderson equation says you can do this by adding this extra term. And so let's do an example here. So the forward process is this. Now I do the backward process. I do this for the same one as before, so no drift. And so I start here from 2 normal distributions. There we go. And when I evolve this For Planck equation of backward on the Borg equation, the two peak structure emerges from the normal distribution. I could have just shown you the backward movie of the previous slide, but to show you that I didn't do this, I explicitly start from two different initial distributions to show that they do converge to the same target. This is proof that I'm not running.
So there's something in the starting one now going backwards, which knows that it must make two peaks because otherwise you're just doing diffusion in.
Yeah, so this is extra term here. And this term contains the information. This term will make you end up at the target distribution.
So the initial probability distribution was produced by forward evolution from a double peak one.
Yeah.
Right. But if I picked something pretty close to it, which was simply a single peak, it's typically.
But it will produce whatever you start from. So it's supposed to be a reversible process in terms of distributions.
Am I wrong in thinking that if I just picked a Gaussian and then ran it backwards, it won't produce two peaks from it?
No, it won't. No. If you start with the Gaussian and you run it forward, the variance will most likely change, and then you run it backward, and the variance will go back to the initial variance.
But because the whole point is that the middle curve is the one that occurred in the forward process.
But in this case, for example, the drift term, there is no potential, right? So it doesn't know anything.
No, the forward process, no, okay, so that's the point. The forward process knows nothing. The backward process always has this Anderson term in the score. The score is the crucial thing.
Eventually, you have some force telling you.
Yeah, the force telling you where to go. So. Then I also made a movie in dimension, guys. So this is just the backward process. So I start with a normal distribution in both directions, and I will end up with the target distribution. And I'm showing this because I want to show how the score of the drift works. So this is how creating those three peaks. And the score that takes care of this in the backward process, initially it has no structure, it just goes to points to this normal distribution, so to say. But as I run it, the score is changing and it's nudging you towards the three peaks. So there's one peak is here, one peak is here. So it's a very subtle nudge, I have to say. You have to look quite closely. But the arrows flip around and push you in the right direction.
The topological interpretation of what's happening in the score. It looks like you're creating a vortex anti-vortex pair or something like that.
No. I think it's all stochastic, so I think it's fine with topology.
There was some nucleation event at some intermediate time in the score that produced these three worlds from.
Yeah, so that depends a bit on this noise profile, basically. When this G of T or G of tau, which grows sigma to the power T, when is the change happening mostly? Okay. It's not a linear process. So this is why it's called the noise profile, the time scheduler.
Score movie one more time.
Yeah. Very easy.
Interesting transition from one defect to two positive defects and minus one.
Yeah, so here I know the score analytic, so I'm simply plotting the vector field.
Okay.
Time. So
Can I ask actually? So in particular, when you make these movies, you're not sampling from the distribution, because there'll be some more like phase transitions later when you go back to the atomic version of the sample distribution.
yeah, so later I will show you the sample, actually data from say lattice field theory simulations. But we can't solve this Fokker-Planck type equation, so we actually sample configurations and take activation values, and then you see noise as well because you have finite statistics and so forth. So this is the very idealized case where I can solve the Fokker-Planck equation, and I know the score analytically, so it's a fully controlled environment for the lecture. Okay, so where does machine learning come in? Because I haven't really said anything about machine learning. This is just an analysis of SDEs and FPEs, and based on work from 1982. And so the point is, of course, that in general, this score, this extra term, is not known. And it needs to be learned during the process, and it depends on your target distribution. So it's specific to that. And so to learn this score is called score matching. And it's obtained by minimizing a loss function. And so that's where ML comes in. And it's quite simple to explain, actually. So 2 slides is all that is needed in this particular, sorry, for this setup. So let me do that. So the same setup as before, we have diffusion, time-dependent noise strength. This distribution here describes the forward process, backward process. The score is not known. And so we want to minimize the cost functions, quadratic cost function. And this is the quantity, this will be a neural network. So this is the quantity that we want to determine by theta are the parameters of the network. And this should become equal to the score, which we want to know but do not know. So this is the minimization. And the score depends on all the times of the process. So there's an integral over all the times. Here is an expectation value with respect to this time-dependent distribution here. And in particular, it also includes time 0, which is the target data. So score knows about the target data. And so it's a gradient of a function, so it's a vector field. So how do we learn it? So in fact, so there are approaches. So this is an answer to Zohar's question that this type of equation has been studied in the past by Fisher inequality or something. I mean, so there's different ways to try to solve this equation. And the one I'm showing now is the one that works, but there are various routes to arrive to. So introduce this conditional distribution. So we factorize the initial data from this amplitude here. And of course, the time dependence of this quantity is given by the time dependence of this quantity. So that's convenient. And we know, so this, I already discussed this. We know this condition amplitude is given by this. And so we're done, surprisingly. We can take the gradient of the log of this condition amplitude, it's just linear, because it's a Gaussian. And we can substitute this in our top equation there. So we are here. And now you see the reason to put sigma squared in front of it, because sigma squared inside the square, this becomes 2 sigma here. And lo and behold, this combination xt minus x naught over sigma is just the noise vector, just the eta. And so we've arrived at an equation here, which does not have any reference to the original distribution, but basically the score is now matched by minimizing this one. This is quite miraculous, I have to say, but
Okay, how did P0 disappear?
yeah, so P0 is showing this average here, but it's not there explicitly. We only have this amplitude here going from x0 to x. Now, when you sample configurations, you start from samples from P0, but you only learn the score then from later times onward, where all you need is this information.
Gradient of log P, that one knows about P0.
The expectation value knows about P0. The gradient of log P does not know, well, it knows it's conditional on x0, but you do not need to know the actual distribution. So it's conditional on x0, that's the way to say it, and at later time, then that the evolution from that condition to later time is known because that.
So there's the issue that this learns basically to memorize the data set, right?
Well, it gives you a drift that will guide you to the data set. The derivative, yeah. It learns the
empirical. So I guess it's over there written by the Zoom.
yes, yeah. So that's just PT. That's just this the bottom equation. So but it learns this transition, and then you can go forward and back.
It is also estimate density.
That's a good question. Yeah. So then you can integrate this equation to try to do density estimation. We have looked at it a little bit. I don't have anything to say about it. So these are the 2 slides in a way where the machine learning comes in. You have to learn the score, and this is the cost function here. Yeah.
So in the actual applications, right, how do people define it in the space of stock pictures?
It's just nearest. Okay, now I'm confused. Now I have to think how to. No, it's just a functional derivative. No. It's just in nearest neighbors. Say.
Discrete.
Well, it doesn't have to be discrete. It learns it as a continuous function, but you sample it, and it will interpolate where you need it. But you could think about it as on a grid. Yeah, so it doesn't. Okay, now I have to think which space does it live. Yeah, which space does it live in?
If you are in this image, it's R2.
72, that's the C. 3 times the number of pixels.
Yeah,
And
it's
this
space,
actually
I guess.
derivative, you just learned the score, which is already the gradients. Never in the training, you actually need to take derivatives. Different S, which is a vector.
So you don't have that because of snapshots. So we're trying to, okay, so there's no point really to evaluate where it's not. Right?
No, not because of this trade thing.
Yeah, so indeed, yeah. So you never have to compute the gradient. In the simple example I showed before, it's not analytically. Here you just have a vector field. You can go do the job for you.
Actually, the space of images, the space of images is just a vector where you put all the pixels, as numbers and all the colors. So every pixel is a three-dimensional vector, concatenate them. And that's how you represent an image.
But going in a random direction on this description won't be difficult. Won't be very difficult at all.
It will be. What's the difference between a dog and a dog image in this context?
No, it won't bring it between a dog image result.
You're not constrained to the manifold of dogs, so you can easily collide.
Yeah, if there is such a concrete manifold, yeah. I don't think you need to really have a notion of a manifold.
No.
The formulas.
No, and in fact, the question of phase transitions, there are these papers that study diffusion models and find phase transitions to go from a dog to a giraffe. It can be interpreted as a phase transition. But okay, let's go on. Let's go on. So to come back to these two terminology that's used in machine learning, so there's DDPMs, in the diffusion probabilistic models have a linear drift here. And the variance expanding schemes have no drift, so no term here. But both of these can be treated in the same way, and the whole point is also with a linear drift, this transition up to this non-linear. Same principle applies. The point is that both of these equations you can solve. Okay, so this was the introduction. Yeah.
Before you start adding more variables. So supposing I wanted to work with a large band equation with a potential, right? So that the S is control. Now, the forward process is I'm trying to learn the potential from a set of runs in which I increase the noise. So as it were, I heat up the system and so on, right? Now, presumably I need to start with particles which have been drawn from the correct distribution. Okay, and then, so what's the physics behind that so there's some formula for I heat it up and it expands the range of it, and there's some derivative which allows me, it's like the Einstein relation.
It's like I said, yeah.
It's the Einstein relation.
So there would be this one would have fluctuation dissipation relation where the noise wants to grow, but the force tries to drive it back, and you end up with a nice normal distribution. This one is just diffusion, so this one just grows. But
Let's say if you think of this with the machine learning path, maybe, right? So then you would have samples at different times. So it's an initial thermalized distribution or equilibrium distribution, then time dependent noise,
Yeah, okay, with the machine learning heads up, it's interesting because we don't know. That's my vague thought. We do not know the manifold in which the data lives at all. And in a way, this is many holy grails in machine learning, but if we would know how the data is encoded. So we would learn the grade, what we are learning is kind of the gradient of the log of this distribution.
So I should probably explain the stability of my confusion at this point, which is, so I'm, in my mind, I'm imagining I've got this potential, let's say some well, and I've got noise. And as you increase the noise, I'm trying to learn the shape of the potential. On the other hand, I could increase the noise at different rates. So one is a quasi-adiabatic, the other is very non-equilibrium. So how to learn the potential seems like a problem that depends on how quickly I heat it up.
Yeah, so you don't, during this heating up, you don't learn the potential at t equals 0. You learn the kind of a time-dependent potential that deforms from your target potential, your initial potential to maybe no potential at all, or just the Gaussian. So
And is there not a timescale issue? How quickly, for instance, I get rid of the potential versus?
I think so, yeah. So that's why these noise schedules are quite important, that you have to reach, thermalize correctly to the right potential and not do it too quick.
So there is that issue, right? But
Can I ask a really naive question? So why is it that that's a better thing to do, to try to learn the gradient potential and to try to just learn the initial distribution? Obviously, if that had worked, something.
Yeah, okay, so I see. Yeah, so one answer to that is that in terms of tractable, is that as you can see, we don't need to know the normalization of the distribution because we take the gradient of the log. So normally P is 1/z integral of all things. So if you want to learn the distribution, well, you also have to learn the normalization, which is the integrated of the whole of the data manifold. So the advantage of the fact that you only have to learn the gradient of the log of the distribution is that the normalization is not required. It's in general, so HMC has the same, because an HMC sample, and you're sampling correctly, so to say. Other methods, the numerical method, you sometimes have to know the actual normalization, and that's big problems. So that's one answer.
Integration in the actual implementation in the some.
Yeah, so this is a sum, and the time steps, maybe 1,000 steps here, and they're not uniform. And you can sample. You can also sample the time steps here.
So you have to, for one single path of the network, it's sequentially. You have to conserve that sequentiality.
Well, this is a very interesting question because in the forward process, you don't have to do it because this solution is valid for all t, so to say. So you can jump from time 0 to time t here or time t here. For the backward process, you have to do it in causal because you want to generate the right distribution. That's a very good question.
So one more question. So this S beta, is it so is this one network where the time point is an input, or do we have like reach time point in another network and we create an input reach time point?
No, it's one network where this is. I'm going to look at Dia as my student who does all this stuff. So is an embedding or something?
The T.
The T.
Yeah, it's a time embedding to make sure at these times that it knows the score.
Okay. To direct all these different questions. Okay, let's move on. So, so the reason I got into this is that there's a relation to stochastic quantization. Already into that. So just for those of you who do not know lattice field theory, basically it's a way to study quantum field theories on a Euclidean space-time. In space-time, we're doing simulations, and typically you generate configurations using importance sampling. It's possible because we know the action, so we know what we want to simulate. And one ultimate motivation of this whole program is that, okay, we all want to do QCD. Well, we are doing QCD in normal, conventional ways, but QCD is still hard, still an outstanding challenge. The reason it's in four dimensions, so many degrees of freedom. So the gluons live on links, quarks live on sides. Light quarks are numerically expensive to include because you have to invert a matrix, which is not well conditioned. Chiral symmetry is difficult on the lattice to preserve. Of course, you have to take continuum limit, infinite volume limit. So, and then HMC and other algorithms are still not completely optimal when you want to simulate very close to a phase transition or very light quarks. So this is a major field of research. Lattice QCD with current algorithms, it runs on national HPC facilities. So this is an endeavor which has a lot of people working on it. It's very worthwhile. But it's interesting to think whether there are alternatives to hybrid Monte Carlo, which may be able, where you may be able to avoid or evade some of these problems. So that's an ultimate motivation. We're not there at all because we're doing two-dimensional scalar fields and fermionic models and U1 gauge series in 2 dimensions. So we're very far from this, but this is ultimately a driver. And so in lattice field theory, very basically, you also create a sequence of configurations to estimate absolute pools. And of course, your algorithm should create configurations that are statistically independent and statistically balanced and ergodic and so on. We know the Boltzmann weight because we know our Euclidean action here, so that's very good. And so hybrid Monte Carlo is by most used algorithm. Say some issues in certain regions. But the point is there's a whole class of algorithms that can be used, and historically, before hybrid Monte Carlo from like 1987 or so, before hybrid Monte Carlo, there was an approach called stochastic quantization by Parisian Wu in 1980. And there you generate configurations by solving a stochastic equation, just like the one we just discussed. So if I take the field equation I've shown before, the one that comes from the diffusion model with this gradient of the log and time dependent and so on and so forth. If we now kind of ignore the time dependent for a bit, or not even, if we just say that this distribution can be written as e to the minus s, which is always possible because this should be positive, negative, so I can always write it like this with some normalization. Then the gradient of the log is this minus derivative of the action, and I end up with this equation. So I can always write my diffusion model equation in this way. And it turns out that this equation is very familiar, as I said, to lattice field theories, because this is the equation you do few modifications when you do stochastic quantization. And so stochastic quantization is a fast integral quantization in a fictitious time. As I tried to mention a few times, in our case, in the field theory case, the distribution is known. And so the gradient of the log of the distribution is just the gradient of the action. There's no time dependence here. It's fixed. And we typically don't use the G term there. Conventionally, there is a square root of 2 here, but these are all kind of minor details. But the point is that if you solve this equation, you also generate field configurations which are distributed according to this distribution. And so that's the price, yeah.
So basically, you just plug in P is equal to E to the minus S.
Yeah, yeah. So that's what we do in field theory. We know P, plug in E to the minus S, and you solve this equation. It's easier in a way than the diffusion model because you don't have to learn the score, and there is no time dependence here. The drift is fixed.
You talk presumably about how this compares to your 2D work where you do use the diffusion model.
Well, yeah, so this is one thing you can do. I won't talk about that, but we did it in one paper where we use hybrid Monte Carlo, we use this stochastic quantization, we use the diffusion model and compare the quality of data predictions of observables.
And I guess this has the advantage of being supernatural from the point of the field theory you're trying to simulate, but the diffusion model learns faster, or
no, so this is a very good question. So what could let me
what's the advantage is what I'm trying to get
yeah, so let me come to that in a bit. Sure. So let me first finish this. So there's a few similarities and differences. So in stochastic quantization, the drift is fixed. It's determined from a non-action. Okay, as I said, we don't have this noise variance, but you can generalize this if needed. And the other kind of interesting philosophical difference is that you really look at the long time evolution. So you let configurations thermalize and you take measurements every so many steps. Whereas in the diffusion model, you both the drift and the noise are time dependent. Also, you learn from data, which is different. And you do many short runs. The evolution is from 0 to 1, forward, back. But the training is forward, backward. The the application to generate configurations is only backward. Very short, many short runs going backward. And just as a side note, which I already alluded to, I work on stochastic quantization and QCD and series with a sign problem. Well, I know there is no kind of really old.
One more question, just so we have on history. To what extent did Parisian move have quantum theories in mind?
They had quantum theories in mind.
They did it, it's in the name, but I guess my point is you could in principle use it for any action, e to the minus s, regardless of whether.
Yeah, but their application was lattice field theory. And in a way, historically, you can see stochastic quantization as one of the algorithms on the way to hybrid Monte Carlo. So what I didn't say is that stochastic quantization as is not an exact algorithm. There are finite step size corrections, and then hybrid Monte Carlo include essentially does either you do deterministic Hamiltonian dynamics, or you do some stochastic dynamics, and then you do an accept reject step to make it exact. So
it's like typing your diffusion model into the standard Monte Carlo, but here you can do it with stochastic.
yeah, exactly.
Well, I should also say, this is model A dynamics and statistical mechanics, and where you see once the connection between statistical mechanics and field theory is clear, then it's kind of an obvious thing that to get e to the minus s, you would, like just doing real-time model, statistical mechanics without a conservation law, but a scalar field, just with one.
It's obvious, yeah. It is interestingly, of course, things are obvious in hindsight.
I just meant that
particular application.
Statistical mechanics, it was already.
Yeah.
That may be years, yeah.
So you can make a graph like this, basically, where we have a theory. Now we have a physics application, so we know the theory we have. And so we could immediately apply stochastic quantization, just take the derivative and create configurations. But an alternative route now is to say, well, we have to, the people have to learn from data, so we use something like HNC to create configurations, and then train a diffusion model during the forward process, and then create new configurations. Now, the obvious question that Jim asked is why would you go through this route? Because it seems like a lot of effort if you can just go like that, or even just use HNC, because then you also don't. And the idea, of course, is that there are some advantages by doing the diffusion model route. For instance, it may be really expensive to create configurations. So maybe you can create a finite data set here, which is representative of the space of configurations. Then you train a diffusion model, which is much cheaper to run. So there's one possible advantage. Cheaper. The other one is that you can change your parameters. So you can do some conditioning and a bit like reweighting. Say you can train your diffusion model and then change some of the parameters in the action, so to say. So you can create new type of configuration. And the one we're working on now, as one example, is for fermionic models. But if you do fermions, and you use the standard HMC, you have to create invert the fermion matrix for every update, which is expensive. But the diffusion model for some fermion models is just a bosonic model, like a scalar field. And so the actual update, you don't need to do it. The fermion matrix has completely disappeared. You just have a drift term that represents that particular aspect of the model. So these are all, I would say, exploratory directions. But there's scope that this indeed would maybe be faster or better or avoid some of the problems.
So the stuff, the results that you've shown us, that you've sort of derived for us, are all in continuous.
Yes.
Yeah. But when you run this, you're going to be running it in discretized. The backward process and diffusion. So does that generate discretization errors?
That's a good question. I think it does, because it's just a Langevin equation, basically. It would have step size linear.
So you have to do a final step where you do an accept reject on
the
configuration that you get in the end.
That's what we do now, but for the results I will show in a minute, we didn't. And one reason is that the step size is in fact not uniform in the backward process. It's going to 0 when you reach your target. So you're taking away the continuous time limit when you reach your target. But in principle, of course, it has to be like the simple discretization I showed in the beginning has a linear deviation. Okay, so this is going back to the 5 to the 4 theory. This is what we did. So all good. All good is the question, because this goes to the before the next topic, then this in a way addresses Jim's question, say, in real world applications, we don't know the distribution, we only know the data. Physics application, we know the theory we want to simulate. And so hopefully we can use this. And in our recent paper, we have two ways to implement this. One is what's called physics condition diffusion models, where we change the beta parameter in a lattice gauge theory, U1 theory, and we train the diffusion model on one value of beta, and then apply it on different values of beta to generate these iterations across parameter space. And then, in a way, relate to your question, because it's just a Langevin process, so you can make it stack by including a metropolis step as well. So in a way, the merging of the ideas from machine learning and from physics may lead to new directions where we can benefit from both. Okay, any questions?
Your 5-fold theory is the analog of turning off the 5-fold stone and ending up with a Gaussian. Is that the noise limit or just turning off everything?
No, that's a very good question. So the kinetic term is also switched off, so to say. It just becomes Gaussian at a point, at space-time, every point in time. And I'll come to that now, actually. So,
From a field theory viewpoint, might not it be useful to just dial the 5-fold?
it could be, yeah. So you could put in more information and say, we know there is a kinetic term. So
At least the Gaussian is doable.
the Gaussian is doable, yes. Yeah. This is possible. No, okay, the interesting thing is, like in the Three Peaks movie, you want to be able to create those 3 peaks. And so if you somehow constrain your drift to be, say, local, or like in a kinetic term on the lattice, so tridiagonal, to say, then maybe you are too restrictive, because maybe then you will not be sufficiently ergodic to sample the space. You actually want to have a distribution which has very little structure, is very broad, and then the right structure should emerge from the process. If you know, yeah, so I can argue both ways, but that's kind of the philosophy, that you don't want to impose too many restrictions, because then you might run in exactly the same problems as hybrid Monte Carlo does. Okay, so it seems to work, but I talked a lot about the variance. Yeah.
I don't know if they're happy. No, it's special. The extraordinary special part of noise brings you to thought for another.
Yeah, I don't know. I don't know much about this effects or how to project levels.
You see the sorry, face diagram.
Yeah. I don't know. We can talk about it. So just in the last 15 minutes or so, 20 minutes, a lot of machine learning literature really focuses just on the 2-point function, on the variance. The variance has to grow. You want to end up with a normal distribution, and you can convert it to small, which is great. But of course, as was emphasized yesterday, of course, a lot 2-point function is Gaussian. Gaussian is free fields. And in field theory, we're really interested in the higher endpoint functions because they contain the interactions. And we want to know that the interactions, we apply this to lattice field theory. 2 minutes and 15, 2 meetings in 15 minutes.
Please stay with us.
Yeah, I'll stay here. And so we want to really now understand whether the higher order moments, and particularly the cumulants, I mentioned as well, are captured correctly in this approach. Because if not, then we can't describe an interacting field theory. So I'm going to go a little bit quick, I think. But so here are the equations again. We've already seen this. I'm going to solve it now for both variance expanding, no drift, and DDPMs, the linear drift. In one line, it's very easy. This equation is the solution is very similar to what I wrote down before. This is X naught, the initial condition. This is the integral of the noise times G. But if there is a drift, you have an additional factor here where the drift appears in the exponent. some integral here. And you can see that this solves the equation. If I take a time derivative, take a derivative of this f, which brings down k, so it satisfies that equation. So this is the solution. And well, you can already see one difference between having no drift or having a drift. If you have no drift, this k there is 0, so this f function is simply 1, and then the initial condition is still here, doesn't go away, but the noise is growing. Whereas if you have a drift, this function here is an exponential in time, and so the memory of the initial condition goes suppressed. So there's an exponential gain here. That's the main difference. And then you can compute the second moment or the cumulant or the variance. I always, it's hidden here, but I always have normalized the data sets such that the mean is 0. So my second moment is the same as the second cumulant. And it grows, it depends on time with this integral over this functions. Now, as I said, in the literature, this is what people look at. They look at the 2-point function and mass. But in field theory, we want to look at higher endpoint functions, cumulants especially, and we can just work it out. So let's take the cumulant, third cumulant, fourth one we all know. So this is the fourth moment, so x to the 4, and you can see it has an initial condition. It has a mixture of noise. An initial condition, and there's noise squared. This was followed from the fact that the noise comes from the normal distribution. And then we use Wick's theorem. The cumulant is given, phi to the 4 connected is phi to the 4 minus 3 times phi squared. This is what we know, Hartree-Fock approximation and so on. And so you can work out the fourth cumulant here, and turns out it's equal to the fourth cumulant of the target distribution times this f function. And the same is true for the higher order cumulants as well. So the fifth cumulant, the time dependence of the fifth cumulant is given by the cumulant of the target distribution times this f function here, and so on. And so this means that, okay, in the DDPM, where this f function goes exponentially to 0 in time, all these cumulants go to 0. And so only the variance survives. All the higher order cumulants go to 0. So you end up with a normal distribution. But in the variance expanding scheme, this f function is 1, and all the cumulants are exactly conserved in this diffusion process. And so the whole picture that I was sketching to you, where we say you go from a complicated distribution to a normal distribution back, in fact, it's not exactly correct, because the cumulants are up there, always lurking in the background. They're not very visible, because your second moment grows very large, so that seems to dominate everything. The cumulants are still there.
This is theoretically guaranteed in the minidrifts.
Theoretically guaranteed?
In this epic.
Yes, exactly. And I'll show numerics for this.
Sorry, so to the extent that this is true from your lattice applications, outside of this, it just seems like you up the error that you would get from discretization in time, you would be able to use this as a theoretical guarantee for the full field theory and not have to pipe it into a standard model.
Yeah. So the question you should ask is, what happens now if you start? What happens if you start with a normal distribution? All these cumulants are 0.
Yeah.
And I've shown that they are conserved. How this seems like a mismatch.
Cumulants are conserved for
all time. And of course, the point, the score implements the cumulants. So the score quickly recovers these cumulants in the back process.
the preservation of the initialization cumulants.
Yeah.
So can I actually ask, in the numerical discretization, what happens to this? Do the cumulants actually decay? Like you actually lose them? Or?
In the DDPM, you lose them. In the variance expanding scheme, you preserve them up to noise, up to statistics. I'll speed up a little bit, because this is really kind of interesting, but time is running out. So, but I think it's actually really interesting. So there's an exact proof to all orders. So we can have the generating functional for the moment. This is the source, this is the degree of freedom, and then cumulants come from the log of this. And the average here is a double average, is an average over the noise, which is Gaussian, and an average over the initial conditions, which is X naught, B naught. And because we can solve the equation in time for this, it's just simple algebra to show that this 2-point function separates out and the rest of the target distribution is still there. And so if we look at the cumulant generator, it has this very nice structure that if you differentiate twice to get the variance, you get this quantity that grows in time and dominates, plus the initial 2-point function. If you look at higher order cumulants, this term does not contribute. So you only are left with the higher order cumulants that were in the series originally. So this does exactly what I just proved by one cumulant at a time. It's to all orders. And now let's do some numerics to show you what it actually shows. So this is some numerics now with 2 peaks, 2 Gaussians. This is a nice model because it's exactly solvable. All the even cumulants are non-zero. And we also know the time dependence score analytically, so we can test the diffusion model in that way. And so this is in the variance expanding scheme. This is a 2-point function, and indeed it just grows large. This is what it should do. The variance should grow and dominate everything. If I go do the backward process, it comes down from large and it reaches the expected value. So this is normalized in such a way that this 0 means it. So it does exactly as it should. This is the one with the drift. And here we also know the time evolution of the second moment, given by that equation. But here you see the influence of the noise actually. So here there's a finite number of configurations that are being generated, and it kind of follows the analytic answer, but it's quite noisy. And in the same way, in the backward process, it starts out really quite noisy, and then goes to the expected answer. Now, it doesn't look very good on this plot here because it doesn't look like it's 1, but I'll show you a table with numbers to show that it does the properly answer. Now we go to the higher order cumulants. So 4, 6, and 8 cumulant. This is the model with the drift, where all the cumulants should go exponentially to 0. And indeed they do. This is the forward process. All these cumulants go to 0. So that's great. So the final distribution is a normal distribution. When I turn the process around and go backwards, they come and they exactly reach the prescribed value from the target distribution. So the backward process recovers all these higher order cumulants. That's exactly as it said on the tin, as it is. This is probably the most interesting one. This is the model without the drift. Here the cumulants should be preserved. And what you see is that in the forward process, say, initially they are preserved, but then you hit a kind of effect of finite statistics, because these higher cumulants are differences between fourth moment and second moment squared. But the second moment is growing, so you have a difference between very large numbers. And if you go to the 6th cumulant, 6 moments minus 4th moments times second moment, blah, blah, blah. So this is a numerically sensitive quantity. And if you increase the number of trajectories, so this is get real numerics with trajectories, and you can see if you increase your statistics, you get better and better coverage. So theoretically, the cumulants should be conserved. Numerically, they are conserved up to cancellation, basically. If you turn the process around, initially the variance or the noise is very large. So initially there's a lot of noise, so to say, so you get this kind of noisy behavior, but then it reaches the right values. This is a table then just to show you that if you look at these different cumulants exact, just from the analytical expression of the distribution, data means generate a finite number of configurations from this distribution. And then the variance expanding scheme in the DDPM. And basically, you will see extremely good agreement. The variance expanding scheme slightly outperforms the whole scheme, but these cumulants are learned correctly. And that's what we want for field theory application. We want to learn the higher order interactions.
I just want to make sure I understand, because it's very different from what I normally hear from the lattice community. So you have a different type of theoretical guarantee that you're getting with the right target theory than the normal one, which is just right.
Well, yeah. So I didn't. So the normal consideration is to show detailed balance and blah blah blah.
Yeah.
Markov chain Monte Carlo. So here I didn't use any of that language.
Yeah, exactly.
Yeah.
But you still have a theory guarantee because you get all the high order cumulants right.
Well, so the diffusion model has this, does it correctly,
Yes.
but it doesn't, I don't think you can conclude then that if you would actually apply it in real big simulation, that you still have to verify that there has to be some form of detailed balance. I don't think it's enough to say the method works to the extent that you trust it in the same way that you trust hybrid.
Is it an experimental result that the cumulants match, or a theory result that you know is like guaranteed behind it, and then you also happen to view that the
Exactly. No, there's a theory result that the cumulants match, and then there's an experimental numerical experiment to check it out. I know it's great.
Can't you then just throw out the whole Monte Carlo thing that people normally do because you're just doing the diffusion?
Yes.
Okay.
So, yes, but we have to be careful. I mean,
No, I mean, I don't know. I sometimes talk to a lot of people, we have these exactness guarantees, and the answer is yes in the infinite statistics limit, right?
but it's the same is true here, of
No,
course.
exactly.
Yeah.
But if you had a comparison of how the discretization error compares to the not being an infinite statistics, it could be that you just win and you have a totally different scheme. I mean, it requires an analysis, but
But yeah, you could learn this. You could learn the score slightly wrong,
Yeah.
and then you get slightly the wrong result. So then you still need to do something. I mean,
oh, I see.
it's a numerical. In the end, it's a numerical training.
So unless you have control over the errors in the learned score.
Yeah. Let me.
Ask a question. You're turning something on and off. I mean, there's a time scale component also, so that also, in which will enter your learning score.
Let me go to the field theory then. So we did the same analysis in the two-dimensional scalar field theory. Equations we have already seen. We can compute the moments as well. These are all at the same lattice side x, so spatial invariance is independent of x. You can do the same proof, and this is actually, I like this a lot because this is not the moment generating function or the cumulant generating functional. And this is the integral over the initial distribution e to the minus s. So this is actually the full path integral. And so in your diffusion process, forward and backward, the full path integral is always there with sources. And so when you generate these cumulants, where you have exactly the same structure, the second moment depends on this noise contribution, the higher moments do not, but the path integral is always there during the diffusion process. If this function goes exponentially to 0, it basically means that the field amplitudes are all squeezed to 0, and you just end up with the Gaussian theory, but this is the variance. If you're in the other scheme where this function is equal to 1, the full path integral is always there in the background. And this is why it's a proof. Yeah, no, it's a proof, but not that we know it. No, but this is why you can generate these cumulants in these moments, because the path integral is always there. So we applied this in the phi to the fourth theory, second and fourth cumulant, forward and backward, and then the sixth cumulant, forward and backward. This is in the variance expanding scheme where you suffer from this incomplete cancellation, which indeed shows that sixth cumulant is constant up to this cancellation. But the backward process recovers this very, very quickly.
Then if I want to sample from a Gaussian and just run the backward process, how terribly will these two Gaussians change? Let's say in the previous example, I mean, how long it is then to run the backward process from a true Gaussian?
So if you start with the normal distribution for the backward,
yeah.
that's what's done here. That's what's done. So the backward process here starts from a Gaussian because you do not know what the cumulants are a priori. So you don't want to. If you would have to build them in, you would be screwed in a way.
And that was the previous plot.
Yeah. So that's the nice thing that it learns these higher order cumulants very, very quickly, but you don't have to do them.
How many target cumulants did you do perturbation theory, or did you?
No. I know that. Okay, that's exactly the slide. So we know the target cumulants because we have the agency data. So we have you simulate them. You simulate it anyhow for the training data, and so the cumulants from agency are these, and then the trained diffusion model gives these, which is basically spot on. So. Actually, the method works. There's no except reject here needed. This works. So this is why we're quite enthusiastic about this. Let me say that. I'm gonna, which is the big hand and which is a small hand. So we've extended it to U1 gauge theories. We also apply to complex actions, which I won't talk about, and also the fermionic models, because that's interesting because you don't have to do the fermion permanent or inversion anymore. There's one thing about the exactness. So this is the backward process. Normal to the target. There are two things happening in this plot, so ignore this one. But you can make it exact by saying, I've now generated configurations, I'm nearly at the end of my backward process. Then I can include those configurations in a Markov chain by including some metropolis steps. So this is known in the Langevin community as the metropolis adjusted Langevin algorithm, or MALA. That's basically an accept reject, which takes into account both the transition amplitudes from here to here and the exact target distribution, which we know analytically. So you can do a metropolis Hastings step based on this probability. And that makes it exact based on this algorithm from the 90s or 80s. So that's, well, that's in the paper, but there's a lot of work to be done to extend this. Okay, so I'm going to skip the stochastic quantization, which I know is my personal hobby for a long time. So machine learning is, I think, fascinating playground for theoretical physicists, and both it's interesting to view it as a way where we can apply theoretical physics knowledge to better understand machine learning algorithms. And of course, ultimately, we also want to do research questions like field theory and see if we can contribute there. And so this talk was about diffusion models, essentially a new approach to generate ensembles in field theory. You do have to learn from data, so you need high quality ensembles to begin with. From a theoretical perspective, it's closely related to stochastic quantization. And then we've shown that indeed you can compute higher endpoint functions and you get the correct answer, which all builds of confidence. That this method is useful to explore further. Okay, thank you.
Yeah, we go back to the table and show this in a few minutes.
Like the evolution.
Comparison between the HMC and the actual numbers. Okay, so these 10 to the 5 configurations, this is 10 to the 5 HMC configurations, and then 10 to the 5 diffusion model configurations generated from the machine that learned from the HMCs.
Yeah, but ideally, so I don't remember exactly here, but ideally you train your diffusion model on one set of HMC configurations,
yeah.
And then you make a comparison on like a test.
Of course, yeah, but it's trying,
But the statistics is the same. It's apples and apples by using the same statistics.
And in terms of time, I mean, this is trivial theories, right? But in terms of timing, I mean, it takes you a laptop a certain amount of time to get the HMC configuration.
Yeah, so we're not yet. I have a not convincing answer yet that one is faster than the other because the models are so simple that we don't have time.